Suppose there's a galaxy-wide intelligence test being conducted and we just got our invitation to put out an entry. What does the test ask for? A number. Just a simple number. In binary, of course. It says nothing else. Is that some sort of a joke? It may very well be. Nonetheless, we decide to turn in because this is a matter of our place in this galaxy. So what number should we choose that would show the level of development our civilization has made in understanding the world around us? Okay, so we do have a couple of choices. There are mathematical numbers like pi or Euler's number that show up everywhere. So if we send these, it would very much convey that we are more than just replicating species. However, the problem with a number like pi is that it was around for thousands of years. So it may not be the best number if we want to show them how much progress we have made. Then we can turn to physical constants, numbers that pop in when we try to model the world as relationships between different quantities. The speed of light is one of those things that we know from relativity is same for every observer. So we may want to send that. The problem is, what number would we send for it? The speed of light as we know it is based on the definitions of the units for distance and time. That has no more significance in the rest of the universe. For us, with our definitions of meter and second, the speed of light turns out to be this number, 299,792,458 meters per second. But we cannot simply turn in this number without also telling them how our units work. But since the test has asked for only one number, all these physical constants that depend on the definitions of units are not useful. Planck's constant, gravitational constant are all out of the picture. Maybe the test is actually onto something. What we want are numbers that are not only telling us something about the world that is true everywhere, but are also free from our human notions of reality. What we're looking for are dimensionless physical constants. And they're not really as hard to find once you know where to find them. I mean, we can get dimensionless physical constants whenever we take the ratio of the same kind of thing. Once we figure that out, we have again opened up a wide range of possibility. For instance, the ratio of the mass of the proton to the mass of an electron is a dimensionless number that would be same for everyone. If we actually go on to calculate it, it would be around 1836, and we can very much turn that number in. However, it just so happens that we may have a better entry, a dimensionless physical constant that might just be the most fundamental number that we've known so far. The fine structure constant. It's about 1 over 137. It's both beautiful and intriguing. It's beautiful because 1 over 137 and intriguing because it shows up everywhere electromagnetism is involved. And we don't know why it has the value that it does or what caused it to have that particular value. Even though that might just be true for every physical constant, we don't know where they come from. However, the difference here is that because it is dimensionless, every independent civilization would come up with the same number for this constant, no matter how their system of units work. Richard Feynman called it the magic number that comes to us with no understanding. But what is it and why is it relevant? Well, let's dive into a bit of history. In the early 1910s, Niels Bohr came up with this revolutionary model that solved atoms. For a while, it explained very well the observation for atoms with one electron. For instance, hydrogen. When you irradiate these atoms with light, you see specific spectral lines that are unique to each kind of atom. And Bohr's model was very nicely able to explain that splitting of light. When electrons transition from one energy state to another, the difference in energy is seen as a photon of a particular frequency as required to conserve energy. However, later advanced observations showed that there's actually a fine structure to these spectral lines. Instead of one, there's actually two very narrow, closely spaced lines. Arnold Sommerfeld extended the Bohr's model to include elliptical orbits and the relativistic dependence of mass on energy, and was able to explain this fine structure of spectral lines. The combination of constants that appeared in the equations was this: the square of the electronic charge divided by 4 pi epsilon naught, the reduced Planck's constant times the speed of light. And when you work it out, the units very nicely cancel out, leaving behind a dimensionless number, the fine structure constant alpha. Now this model didn't really go that far because, well, electrons don't really orbit, do they? And so this fine structure of spectral lines was later properly explained after the discovery of electron spin and, well, quantum mechanics. However, the constant alpha didn't end there. Even though this was how it was first discovered, alpha made its way into everything electromagnetism. To list some, the energy of an electron, of two electrons situated at a distance d apart, to the energy of a photon with a wavelength d is, well, alpha. The ratio of the velocity of an electron in its first orbit to the speed of light is again, well, alpha. To the extent that our best theory of electromagnetism, QED, quantum electrodynamics, has this constant placed rigidly in it. It was not a regular trick of numbers. As we understand today, alpha quantifies the strength of the electromagnetic interaction. It is its coupling constant. So the fact that we saw alpha everywhere we saw light and electrons is not really as surprising when you consider that QED is a theory of charged particles and its interaction with light. Something that we get from QED about alpha is that it's not really a constant. I mean, quantum electrodynamics models any interaction based on every possibility. So if two electrons are repelled, it could be that a photon will exchange between them. Or what could have happened was that that photon got turned into an electron-positron pair, got annihilated again, and then absorbed by the other electron, repelling them. So you see, there are multiple, actually infinite ways an interaction could have occurred. And in theory, you have to consider the contributions from each possibility. What sort of works is that at lower energies, the contributions from a lot of these can be ignored. But at high and higher energies, they become more and more relevant. How is all of that relevant in terms of the fine structure constant? Well, the fine structure constant is the coupling constant for electromagnetism. It depends upon the energy scales involved. Alpha changes with energy. At higher energies, alpha is higher, leading to stronger interactions. At lower energies, alpha is lower. The value of alpha that we know, 1 over 137, does show up as a limiting case at lower energies. But for instance, very close to the Big Bang, the energies was much more higher, alpha was much more higher, probably about 1. The world around us wouldn't exist the way it does if alpha wouldn't have the value it does. A higher value of alpha would imply a stronger interaction between proton and electron, leading to a small atomic size, making chemistry more and more difficult. A lower value of alpha would have made atoms larger. The value of alpha is very critical to the way the universe works. And even though we have no reason so far to what causes these physical constants to take on the particular values that they do, figuring that out would take us one step closer to understanding reality. Though we should understand that sometimes there is no deeper reason, sometimes there are no secret ingredients. The fine structure constant is intriguing, 1 over 137, and so as the universe it leads to. And so we can happily send the inverse of the fine structure constant 137 in binary for aliens to, well, explore the level of our civilization's progress. Don't limit your secret. It was just a joke. None of that was happening. They were just joking around. But it was good that we dig down that rabbit hole and thought so much about what these constants mean. Thanks for watching.